are going to discuss in detail what are the conditions for active region, saturation region and cutoff regions. So before that, there will be two types of transistor, that is NPN and PNP transistor. This is a symbol. See, whenever NPN is there, so at the emitter the direction of current is outward in NPN. Reason is, whenever there is a diode, whenever it is forward bias, always current flows from P to N only. So that is why in NPN, so base to emitter junction is forward bias, so P to N the current direction. Similarly for PNP diode, emitter base junction is, emitter is P, so it is forward bias, means P to N is the current direction, so that's why it is upward in PNP. Or we can say into the emitter, it is out of the emitter, it is into the emitter in a PNP. Now we will see regions of operations in or modes of operation of a BJT. So there will be four types. Cutoff region, so it is like a off switch. So cutoff means both junctions will be reverse bias, that is current will be 0 approximately. Similarly in active region, it will act as an amplifier, that means a small change at the input, you will get large change in the at the output, so that's why it gives some amplification. Reasons are the emitter base junction should be forward bias, collector base junction should be reverse bias. In saturation region, it will behave as a on switch, so both should be forward bias. Whenever there is a diode is on, it will behave as a short circuit, so it will looking like a on switch. In a reverse active region, it will behave as attenuator. That means input junction should be reverse bias, output junction should be forward bias. That means at the input, if we give some input, so that will be decreased by some amount. So beta times either decrease or alpha times it will decrease. So it will behave as a simply attenuator. Now we have to see what are the equations, current equations in the active region. So we know that the total current is equal to emitter current is equal to collector current plus base current. Now whenever input junction, emitter base junction is forward bias, we know that from the current diode equation, that is IV characteristics, we know that reverse saturation current into e power Vd diode voltage by eta Vt. In BJT, we always take eta as 1. So emitter base junction is forward bias, so emitter current is Is into e power Vbe by Vt. So this is the exponential relationship coming from the diode. Now another two equations from the different configurations, that is IC is equal to alpha times IE plus ICVO. Generally we can neglect this, the minority carrier currents. Similarly in common emitter configuration, is IC is equal to beta times IB plus some minority carrier current. So these two conditions or equations are valid in active region only. Because suppose when there is a small change at the input, you will get some large changes at the output. This is valid in active region only, right? Because so that we'll see later in saturation region what will happen. Now once we know this, so IC is approximately IE by this expression, so alpha is equal to approximately 1. So I can write IC is like this, IC is equal to IS into e power Vb by Vt. That is the reason if there is a small change at the input base to emitter voltage, you will get large change at the output current or collector current. Now so we know that condition, that is forward bias reverse, but generally when the transistor is in a circuit, so what should be the different voltage levels for the any transistor? If it is taking as a NPN, emitter base junction should be forward bias. That means the cut-in voltage of a diode is 0.7 volt for silicon, so VBE should be 0.7 volt. Now collector base junction should be reverse bias. Now collector is N terminal, N type semiconductor, base is P type. So when it will become reverse bias, when VC is greater than VB, that is N, for N type semiconductor we have to give more voltage compared to base, so that's why VC should be greater than VB or VCB is greater than 0. Generally sometimes we will see VBC should be less than 0 in NPN, so if we multiply this minus, that will become VBC less than 0. Or if these conditions are not, we cannot find, suppose if we find directly VCE, whenever VC is greater than 0.2 volts, then also we can say that it is in active mode. Similarly, for PNP diode, this is opposite. See, emitter is at P and P. So emitter should be greater than base by 0.7 volt. Similarly, for collector base junction, VC should be less than VB. Why? Because VB is, our base is n-type semiconductor. So for n-type we have to give more voltage compared to the collector. So that's why VBC is greater than 0, or we can say VCB is less than 0. Or so it is not VCE, it is VEC should be. So take mod, right? So in this case VCE, in this case VEC, right? Now for our saturation conditions, what is the voltage levels? So for VB, whenever it is forward bias, it should be either greater than or equal to 0.8 volt. So generally, to differ from active region, it is 0.8 volts. Generally we can take it as 0.7 also, because for forward bias region. For the collector base junction should be forward bias also. So we have the voltage levels of VCE sat is equal to 0.2 volts. But these two conditions are not valid in saturation region, right? Why? Because whenever there is a two diodes, that is P and P, or a transistor P and P, so whenever these two are short circuited, right, so these currents will never depend on the any voltages like this, right? So that means these two conditions are not valid. So what we will find is beta saturation, that is we are forcefully assuming that this transistor is in a saturation region, then find IC by any, KCL, KVL using, then IV find, then we can say that beta force or beta sat is equal to IC sat by IB sat, right? So in the next lecture we will see, for a given circuit, suppose the circuit is given and find the region of operation. Suppose some circuit is given 1 kilo ohm, 10 volts, 2 kilo ohm, 10 volts, right? So find the region of operation of this transistor. So this type of circuits we will see, and these type of questions will come and get frequently, right? To find the regions of operation for a given circuit and given the, so what is the transistor operation or mode. Now find the region of operation of for BJT in the given circuit. So in the gate they will ask more generally either find mode of operation or find IC or VC, etc. So for any circuit, to solve the either to find the operation of BJT or find the different voltages, so there will be two methods always. So first method is assume that transistor is in active mode, find IC, IE, IB and VC, VE, VB. We know that for active region VBE should be 0.7 volts and VC should be greater than VB, right? If these two conditions are satisfied, we will, whatever we assume, that is right. Otherwise the transistor is in saturation, right? Now the moment it is in saturation, so these values are not valid. So again we have to find that, assume it is saturation, find the voltages and currents. Similarly, the second method is assume that the transistor is in saturation mode, find the currents and voltages. If the given beta is greater than the what we found from this circuit, that is beta forced. Why it is called beta forced is we forcefully assume that the transistor is in saturation mode, so that's why it is beta forced. Once we get IC and IB, find the beta value. If this beta what we found from the circuit is smaller than the given transistor beta, that is it is in saturation mode. Otherwise the transistor will be in active mode or any other region also we can tell. Again we have to, suppose this is not satisfied, so again we have to assume that it is in active region, then again we need to find the voltages and currents. Now how to find? See, it's a very simple one. So the moment when we assume it is in active region, so the base to emitter voltage should be 0.7 volt. Now this is the base terminal, so this is the base current. Always for any analysis in analog electronics is only either KVL, KCL, nodal analysis, mesh analysis. So I am applying a voltage KVL, Kirchhoff voltage law. So minus 2 plus IB into 1 kilo plus 0.7 is equal to 0. So from this expression I will get IB is equal to 2 minus 0.7, 1.3 by 1 kilo, So this will become 1.3 milliampere. So I know beta, so I can find IC. So I know IC is equal to beta times IB. So beta is 100, so 1.3 milliampere. So this will become 130 milliampere. The moment we got 130 milliampere, it is out of the range of the transistor parameter. So we can say it is in saturation, but anyway we will find the voltages also. Now see, this is grounded, so VE is grounded. Now how to find VB? Right, anyway VB is 0.7 only, but I will find, see, IB is 1.3 milliampere. So 1.3 milliampere into 1 kilo, so this will become 1.3 volts. The remaining is 7.7 volt. So input is okay, but we will find what is the VC value. So VC, what is VC? 10 minus this current into this resistance. So I can say generally we will write like this: VCC minus IC into RC. VCC is 10 volts, IC we got 130 milliampere into 2 kilo. So kilo milli cancel, it will become 260. So it is minus 250 volts. So VC should be, actually it is greater than 0.1, but now VB is greater than the VC. So that is the collector base junction is also in forward bias. So emitter base junction forward bias, collector base junction is also forward bias, though the transistor is in saturation mode. Similarly, for the next transistor, we find like same circuit. I have changed the 10 kilo ohm resistor. So again assume that it is in such active region, so 0.7. So again this is IB. So find minus 2 plus IB into 10 kilo plus 0.7 equal to 0. So minus 2 plus IB into 10 kilo plus 0.7 is equal to 0. So what IB will become? 1.3 by 10 kilo. So this will become you can say 0.13 milliampere. So this is IB. So what can be IC? So 100 times, that is beta times IB. So 0.13 milliampere. So IC will become 13 milliampere. Now again we can tell, so if it is more than 10 milliampere, I can say it is in either saturation region, but anyway we will find the voltages. So which is here is VC. So what is VC? VC is 10 minus 13 milli into 2 kilo. Again it will become 10 minus 26, so minus 16 volts, so which is not possible. So that means this junction also in forward bias. Again the transistor is in saturation only, right? So this is how to find the modes of operation. Next I am taking one more circuit. It is like this. So it is increased to 100 kilo ohm and one resistance is added the emitter, and this is reduced to 1 kilo ohm. Now again this is IB, this is IE, and we are assuming that the transistor is in active region. So assume that active region of transistor. This is assumption. Now apply KVL. So it is minus 5 plus 100 kilo into IB plus 0.7 plus, so the previously it was not there, now it is there, so I have to apply this IE into 1 kilo ohm is equal to 0. So this is one equation, but we are having IB and IE. So we know that IE is equal to IB plus IC. Again we know IC is equal to beta times IB. If you substitute here, I will get IE is equal to beta plus 1 times of IB. Now I can replace this IE by beta plus 1 times of IB. Then I can take IB common. So IB will become 100 kilo plus beta plus 1 times of 1 kilo, which is equal to, this is 5 which is going outside, so 5 minus 0.7, so that will become 4.3. So what is IB? 4.3 by 100 kilo plus beta is given as 100, so beta plus 1 means 101, so 101 into 101 kilo ohm. So total it will become 4.3 by 201 milliampere. So what is this value? 4.3 by 4.3 by 201. 4.3 by 201. It is 0.021 milliampere. So IB we got 0.021 milliampere, or we can say 21 microampere, which is IB. Now compared to the previous two questions, IB was very high. Now it is 21 microampere. I know that IC is equal to beta times IB. So 100 into 21 microampere. So what it will become? 2.1 milliampere. Now it is less than our required, so the current, so it should be generally should be less than 10 milliampere always. So there is some conditions we will get. Now I know IB, I know IC also. Now I can find IE. IE is equal to IC plus IB. So it is 2.1 milliampere plus 21 microampere. So approximately it will become 2.102 milliampere, etc. So approximately we can take IC and IE approximately equal. Now, so what is this VC? I can find 10 minus 2.1 milli into 1 kilo. So 1 kilo milli cancel 2.1. So it will become 7.9 volts as VC. Similarly, if I find VA is equal to this current and this drop. So IE is 2.1 milli into 1 kilo. So again it will become 2.1 volts. This is VE. What about VB? I know IB. So what is this drop? So IB we got 21 microampere. So this drop will become 21 micro into 100 kilo. So what is this drop? It will become, so 100 means 2.1 volts is the drop here. So what is the remaining drop? 2.9 volts is the drop here. So 2.9 minus 2.1, so it will become approximately 0.7 or 0.8. So now see, VB we got 2.8, or we can say 2.7 also, no problem. VC we got 7.9, VE we got 2.1 volts. Now VB is 0.7 volt only, so no problem, it is in forward bias. So what should be VC? VC should be greater than VB. So it is 7.9, it is 2.8. So both, that is emitter base junction is forward bias, collector base junction is in reverse bias mode. That means the transistor is in active mode. So whatever the assumptions we have made, that is correct only, right? So again I am repeating. So we need to find either through KVL, KCL, all the currents and voltages. Now once we found that, so the emitter base junction should be forward bias, so it should be VB at least 0.7 volts, and VC should be greater than VB to make collector base junction reverse bias. So that we need to check, right? So I am going to do the second approach to find the region of operation for the given transistor. So in the previous lecture we have seen, we will assume first the transistor is in active region, then we will find the terminal voltages and currents, then we will say that it is in either active or in saturation. Now in this second method, the first we will assume that the transistor is in saturation. So for the saturation region, what are the conditions are? VB sat is 0.8 volts and VC sat is equal to 0.2 volts. That means the circuit will become like this. So VB should be 0.8, VC should be 0.2. Now what we will do here is, by applying KVLs at the input side and at the output side, we will find IB, IC and VC, VE, right? Now, so what is the input loop equation is -5 plus IB into 10 kilo ohm plus 0.8 is equal to 0, right? So by this expression I will get IB is equal to 4.42 milliampere. At the output side, what is the expression is -8 volts plus IC into 1 kilo ohm plus 0.2 volts. So that is this expression. So by this expression I will get 7.8 milliampere. Now in this saturation method we need to find we have found already IC and IB. Now we need to find beta forced, or it is also called beta minima. So the moment we found IC and IB, we will find IC by IB 7.8 milli by 0.42 milliampere. So it is resulted as 18.57. So condition for saturation region is the given beta. So the given beta is 100 should be greater than beta minimum or beta forced. So beta forced we got 8.57. So this condition is satisfied. That is, the transistor is in saturation. That means whatever we found, the current values are the equal. So similarly, already we have seen VCE short is equal to 0.2 volts. See, VE is grounded. That means VE is 0. So VE 0 means VCE is equal to VC minus VE. This is 0 means VCE is nothing but VC only. So that's why VC is equal to 0.2 volt. Similarly in VBE, VE is 0, so VB will be 0.8 volts. Alright. So in this case, see, we can observe VB 0.8 we got, VC we got 0.2. That means VB is greater than VC. That means this is also in forward bias. So this is in forward bias, this is in forward bias. That means the circuit is in saturation. The transistor is in saturation region. Next we will see one more circuit, same circuit with increased resistance at the input. Now beta is 100 only. Now again we will assume the transistor is in saturation, VBE, and we will apply KVL at the input side. So minus 5 plus 100 into IB plus 0.8. So in this expression we got IB 42 microampere. Similarly for the IC, apply KVL at the output side. So minus 8 plus IC into 1 kilo plus 0.2. So we got 7.8 milliampere. Now so we got YC and IB, so we'll find beta minimum. Beta minimum is 7.8 milli by 42 micro. Now see, we got beta minimum is a 185.71. That means this condition, whatever we in the previous example, it is satisfied. Now it is not satisfied because beta minimum is more. That means the transistor is in active region. That means whatever we found, the IC and IB are the wrong values. Now again we will assume that the transistor is in saturation region, then we will find the current expressions. So whenever the transistor is inactive, VB as 0.7 volt only. Then again apply KVL. So IB will become 43 microampere and IC is beta times IB. So now it is not necessary by applying KVL. So I already discussed IC should be beta times IB in active region. So we got IC as 4.53 milliampere. Now how to find VC is VCC minus IC into RC. So we got 3.7 volts. And similarly VB is 0.71. So that means VC now is greater than VB. That is, the collector base junction is reverse bias, emitter base junction is forward bias. That means the transistor is in active region. So this is how to find the regions of operation of a given transistor.